So now I want to take you through a couple of basic problems on geometric sequences. All we're going to need here is to be able to understand the concept of common ratio and apply that concept to, in this case, extending the series. So we've got to find the common ratio and hence the next three terms in this series here, which might look a bit peculiar. It's an alternating series. It's alternating between positives and negatives there. Now, the key thing here, of course, is that we know that it is a geometric sequence as long as the second term divided by the first term is equal to the third term divided by the second term. So 1 divided by -2. And in both cases, we find that r equals -1/2. Okay? So to get to the next term, we would simply multiply 1 by -1/2. 1 times anything is that thing. So the next three terms, well, it would look like this. 1 times -1/2 is -1/2. And then -1/2 times -1/2 is 1/4. Positive 1/4, because you're timesing a negative by a negative. And yes, 1/4 times a -1/2 will be -1/8. Done. Okay, so we just applied the common ratio to finding the next three terms. Here's a second problem. Find the value of x given that x, x plus 1, x plus 4 is a geometric sequence. Well, you might be sitting there thinking, I don't know. But what you do know is this, that the common ratio is given by the second term divided by the first term. So, second term divided by the first term. And that the common ratio is also given by the third term divided by the second term. Okay? Now, how does that help us exactly? Well, gentlemen, what we're saying is that must equal that. That's an equation. That's an equation. So if we solved our equation for x, if we found the value of x, we will have answered the problem, which was to find the value of x. So let's go to another page and try to remember that.
X plus 1 doesn't work.
X plus 4
Plus 4, so
over x plus 1. Okay, a simple property of fractions is this, you may recall. But since you may not, I'll show you anyway. We know that a half is equal to a lot of things, but one of them would be 2/4. Fair enough? Now, if that's the case, a test for equality is this, the cross multiplication test. So 4 times 1 does equal 2 times 2. So what we can do is apply that logic to this equation here, this pair of fractions here. So let's do that. Now what we're saying, gentlemen, is this. X plus 1 times x plus 1, now I do realise that's a perfect square, which will come in handy, must equal x times x plus 4. So all I'm saying is that times that must equal that times that if these fractions are equal. Okay, let's have a look and see what's going on. Well, can I just pretend, well it's a perfect square. I'm going to use the perfect square identity to expand this as opposed to FOIL. And remember, a perfect square goes like this. The first term squared plus twice the product, so of the inside term, so 2 times 1 is 2, times x is 2x, plus the last term squared, and that must equal that, which is like so. Okay, and let's see what comes out now. Well, that's nice. I can eliminate the x squareds from both sides. Now what have I got? Well, slow and steady will win this race, so I'll write 2x plus 1 equals 4x. What I'm going to do is take 2x from both sides. Therefore, x must, and writing it backwards, or the other way around, x must equal a half. That's our answer. X must equal a half. So, going back to our previous screen, if x equals a half, our series in fact looks like this. A half plus 1 is 1.5, otherwise known as 3 on 2, and 4.5, which is otherwise known as 9 on 2. Okay? And by the way, can you see upstairs here that the common ratio, if we just deal with the numerators as opposed to denominators, the denominators are the same, but there's a common ratio for the numerators, isn't there, of 3.
Yeah.
Okay, so it gives me some clue that I might in fact be right. Okay, so can we stop the tape there, please?